My mic was muted. Oh, my mic was muted. 1, 2, 3, 4, 5. That's what happened. So three things I did. I muted my mic, and I muted Discord, and I muted the StreamYard. That was too, like, I didn't remember. Oh my god, I'm getting so many text messages. Okay. All right. All right. So, what we need to do is, so this is the problem. See, this is basically operating a radar or operating a radar or a sonar. So you have to figure things out. I mean, even a radar is simple because a radar, right? A radar, right? You get the beep, and you see the thing moving. You can get a sense of how fast it's moving because you're aiming. Right, so you can get a feel for where the signal is coming from in the bathtub, right? So if you just have a detector of waves, yeah, that would not you wouldn't be able to tell where the wave is coming from. But if you have two of them, then you already have depth perception. So if a wave travels right from there, this detector would go off first and this detector would go off second, so you would know, oh, it's coming from there. That's why we have two ears, two eyes, and even two nostrils. The two nostrils give us a perception where a smell comes from. If you ever notice, if you smell something, you turn your face, you move your head, that actually gives you a feeling for where the smell comes from. So the two nostrils are very powerful. And the same goes for the ears. By you tilting your head, moving your head closer, further, you get a feel for where a certain noise is coming from. Okay. 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 La 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 la. All right. So with two, so let's assume that we have a detector that gives us depth perception, and so it gives us a direction. This is the detector that we have. So we also, besides seeing a wave, we can feel, we can calculate where the direction it's coming from, what the direction from which it's coming. What is the direction from which it's coming, which it is coming. So that's a good start. So we can tell direction. So we should be able. Oh my God, they're not gonna let me work quietly. So okay. Okay, my God, leave me alone. All right. So, so now the next question is, so this boat is going to be, right? We're going to see bobbing coming out of here and bobbing coming out of here. That's going to give us the L perception. We'll come back to this. But also, I mean, let's ignore L for now. Let's just try and get a feeling for V. So remember, like when you see a movie and there is a person watching the radar, it's usually circular, and there's these, and right, you would see the target beep, like it's here, and then it's here, and then it's here, and then it's here. So you can sense, you get a sense of motion, velocity, direction, right? And so you should be able to, but how do you know the distance? Well, so radar is different. The radar is usually rotating, and it's sending a signal, it's sending a wave, and the wave bounces back. So we can calculate the time. But with this boat, we don't have that luxury. Does the boat tell us the time? I mean, it could. The boat could tell us every time it ticks. So let's say we have that information. Let's say there's no bobbing yet. Let's remove the bobbing. That would remove the radar. So let's just ignore the bobbing. Let's just assume that the boat is just a clock. There's just this, and there's waves going. It's the same Einstein photon clock. That is, the waves are bouncing back and forth. But every time, let's say, it hits this or each side, we get a wave coming at us. And this wave tells us, let's say it's the middle of the boat, so we know where the signal is coming from, we know the direction, and we know that a tick just took place. So we can tell how time, but we don't even need that. All we need is a signal to come towards us, and then we can tell how fast the boat is moving. So we can actually, assuming a constant speed, that the velocity is constant, we should say velocities are constant. That's a given because we are in inertial frames of reference. So we're assuming constant velocity. No one can accelerate. Okay. So if we can figure out the direction, but we don't know the distance, so we need more information because it could be very far or very close. So all we can tell is the angle that it came from here, and later it came from here. So if it's 1 kilometer away, then it's whatever. But if it's 100 kilometers away, then it's much more because all we have is the change of an angle. So I don't know. I don't know in the analysis what, like, we can start from multiple, we can have multiple thought experiments or even experiments in the bathtub. We can run multiple experiments and come up with all different ideas. Hmm. Hmm. Let me take a sip of water. Okay, so mm, if we assume, well, we could assume that it ticks every second. We could assume that they're ticking and are ticking in their point of view. Oh, we don't need to assume that because all we need to assume is that we have the same clock. So let's say we have our clock here that is ticking back and forth, and they have a clock on their boat that is ticking back, but it's the same manufacturer, it's the same clock. So if, and let's say we can get the report, we get a wave, a bob every time there is a tick tock. We get those. So we can, we know we know what we know their tick rate. So we can get their tick rate. Right? I'm assuming that the angle here is tiny. I'm not right. Even if the angle is big, we can take into consideration the Doppler effect. But I don't want to get. I don't want to do that now. So all I want to do is just pretend. Is just do the calculation when it's basically very far ahead of me, right in front of me, so that there's a negligible Doppler shift. Okay. So if we get a report of their ticking, that's that's an accurate report because they're ticking exactly, right? So from their ticking, I can figure out their time dilation because I know, oh, this is great because I know that their, right, their their ticking, T prime is their ticking, is equal to my ticking. I can compare it to my ticking, and I know that it's divided by gamma. One, let's just do divided by gamma. We know gamma. So it's just 1 over gamma. Or 1, sorry, it's times gamma. So it's just gamma my time. So I know the rate of time that I'm experiencing, and I know if I know their rate of time that they're ticking, then from that I can calculate gamma. Great. So given t prime is equal to gamma t, so I can calculate gamma. If I know t prime and I know t, let's say I get theirs is once every 2 seconds and mine is one every second, for example. All right, so I know the ratio, and I know that ratio is gamma. And gamma is equal to 1 over the square root of 1 minus v over c squared. So from this I can calculate, so let's assume I know c. I can calculate c in my frame of reference. That's the speed of the wave. Let's say I measured it to be 1 meter per second. So let's put some numbers here. So let's say t prime is equal to 1 tick per 2 seconds. 1 tick. Tick tock. Tick tock. My ticking is 1 per second. So theirs is 1/2. And c that I measure, that I assume c is a constant. So we are assuming a continuous rigid flow of water, or no flow, just rigid water. It's a stiff medium. It doesn't stretch, it doesn't bend. That's why it can move slower or faster. Einstein's bending of space is incorrect. Space doesn't stretch and doesn't bend. If it did, you wouldn't have gravity, because instead of the moon being pulled towards us, space would just stretch and stretch and stretch and stretch, and the moon would we would lose the moon. And the apple, if space could stretch, and then space would try and pull down the apple, but instead of pulling down the apple, space would stretch and stretch and stretch, and the apple would go into outer space. So Einstein's stretching of space is utter nonsense. What you have instead is a rigid flow of a liquid like water, so it has to change velocity. So as it gets faster, it takes up less space. And that's the way water behaves. Water moves faster into the valve. What do you call that opening in the bathtub? When you empty the bathtub, the water flows very fast, or in the sink, in the kitchen sink. The water moves very fast into the gutter, into the sewage at the point of the opening, but it moves very slow, far away. Right? Water doesn't stretch and doesn't bend, but that's a different discussion. So the speed of the wave c, the speed of the waves is a constant. This is constant one. These are different constants, have nothing to do with each other. This is not accelerated, but you see, we can figure out so much just from a thought experiment about a bathtub. This is or a kitchen sink, and this is exactly, and we can actually get further than Einstein got. We can actually prove, hopefully, Einstein's postulate of the constancy of the speed of the wave in every moving frame of inertial frame of reference. So according to the moving boat, they can measure the speed of the waves. They would get the same c that I would get, even though I'm not moving. That's the postulate. That's what we need to prove. Let's continue. So let's assume c is 1 meters per second, and let's assume v. Can we get v from this? Do we know v? We can get v because we know gamma, because we know t prime to t. This is 1/2 over 1. So this is 1/2. So gamma is 1/2. So this is 2. So square both sides. So it's 4. So 1 minus this. Anyway, we can actually calculate it, and we probably should. But let's find out v given, right? Because we know what's given. Now we need to find out v from the given t prime mt that we can measure, right? It's easy to measure t prime. It's easy to measure t prime and t, right? In real life, you have a bathtub. You're in the dark. We don't even need to know the direction. We don't care. We don't need depth perception. We don't need to be bifocal, bipolar, by whatever. We don't need to. We don't need like a true radar dish. We don't need a radar dish, or we don't need to tell where the signal is coming from. Let's say it's basically right in front of us, somewhere in the dark. It's coming from ahead of us. We don't know how far. We don't care because we're getting the boat is sending us every tick, tick, tick. Jesus Christ! Every tick. Oh my God. La 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 la. 1 second, 1 second, 1 second. La 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 la. All right, this is great. This is really good stuff. This is actual progress. Hopefully, we'll be able to prove the postulate from a bathtub. This is going to be so embarrassing for Einstein that I can prove his postulate from a kitchen sink. Can you imagine that? Can you imagine that? Oh my God. And it's so embarrassing for the scientific industrial complex that we can prove the postulate after 100 years, 120 years, that they haven't even thought about this and we can prove it and they completely missed it. Because we can prove it, I mean, we're completing Einstein's relativity. So Einstein's relativity has been incomplete. They keep saying Einstein's relativity is incomplete because of the black hole singularity and because of the quantum, it doesn't fit the quantum mechanics. The nonsense. These people are so nonsensical. There is issues with Einstein's relativity, namely it's not mechanical. So we're going to make it mechanical. We're going to make Einstein's relativity classical again. Make Einstein's relativity classical again. Meaning we don't need Einstein's relativity. It's going to become wave mechanics. There is no more Einstein's relativity, special relativity. And then concerning Einstein's theory of gravity, what he called general relativity for some reason, that, the equations are correct, but the interpretation is incorrect. The interpretation should be that it's a liquid, it's the same liquid as we're assuming here. And that's why there are no particles. Everything is a wave, and there's no issues. I don't see any issues. I never saw the issue with with a black hole singularity to begin with. La 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 la. La 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 la. La 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 la. La 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 na 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 na. La 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 la. Oh, my battery's too full. This battery's too empty. Anyway, this is great stuff. This is amazingly enough. This is the most cutting edge modern physics you can do, in my opinion. Everything else is nonsensical compared to this. This is, oh my God. How many messages can people send over nothing? How many? It's endless and endless and endless messages. This is unbelievable, about nothing, about absolutely. They're driving me insane. No information is being exchanged. No information. No information. And so much texting. God help me. This is worse than Einstein's postulate of the constancy of speed of light and the constancy of the laws of nature. All these postulates, you don't need anything. You don't need special relativity. It's just wave mechanics. Stop the messages. Stop the messages. Stop, please stop. Please stop. No, please stop. Oh my God. Oh my God. Oh my God. Oh my God. This is impossible. Impossible. Oh my God. 1 second. Oh my god. Oh my god. Mm, oh my god. 1 second. Wow, this is impossible. This is impossible. Impossible. One second. Okay, let's continue with life. All right. So, oh my God. Okay, at least confirmed we're gonna get some quiet. Probably for under 60 seconds. More than 60 seconds of quiet, I think it's illegal. I think we're not allowed, as you know, in modern society, more than 60 seconds of quiet. Who heard of that? All right, ladies and gentlemen. Okay, so all we have is one detector. We ended up with one detector, not two, but we are getting the ticks. That shouldn't be an issue. So they're telling us tick, 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 tick. From the very ticks, we can figure out just because of a thought experiment. From the thought experiment, right? We derived gamma. Gamma is derived from a thought experiment. So gamma is derived from the assumption of some constant speed of waves and some velocity of the observed whatever, observed clock. And t prime is the ticking of the observed clock. T is my ticking. Just from a thought experiment, this has been derived. This, which is the same as this is derived from a thought experiment. So when I take the measurements of t prime, I measured t prime as 1 every 2 seconds, one tick every 2 seconds. I measured my ticking, which is, I'm assuming, 1 every 2 seconds. I'm assuming, or I measured the speed of the waves, that is 1 meters per second. I measured it in my frame of reference. Now I claim that the other guy is also going to measure 1 meter per second. We haven't done that experiment yet, but this is the claim that the moving observed clock will also measure the same speed of waves as I am. All right, so we know the ratio. We know the ratio. So let's take this to the next page. So we can take yeah, let's just take this. This should be enough. Let's copy. Next page. So this is the calculation of the bathtub calculation. La 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 la. La 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 la. All right. So what do we know? Let's develop this equation. Let's get let's get uh, let's get v, right? We want to pull out v given gamma. All right. That should be very straightforward. So we're going to take this and multiply both sides by this square root. So we get the square root on top and gamma on the bottom. So we're going to say the square root of whatever is equal to 1 over gamma. La, la, la. Let's just make sure that this makes sense. Their clock is slower. So this number is smaller. Therefore, this is less than 1. And gamma should be less than 1. And this is gamma. So this should be less than 1. So this should be more than 1. But this is impossible. So something is wrong. Is gamma this or is gamma at the top? How does it work with the gamma? I don't know. We can look at the video, this video. We can look at this video where they developed gamma. Gamma was developed from a thought experiment. Where's gamma? Where is gamma? Gamma. There's gamma. There it is. They're not showing it, but this, here it is. So T moving over T rest. Somebody's talking to us. Let me see. Share general. La 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 la. La 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 la. This guy. What is going on with this guy? He's just annoying. Maybe I should just mute him. Like, can I mute him? I don't want to hear his messages. This guy. There's no way. Oh, I can block him personally. Profile, mention, message, call, add note, change. Because this is not server block. Block. Are you sure you want to block? Blocking this user will also remove them from your friends list. Yeah, for now. All right, let's continue. We were watching a video, this video, or at least this conclusion. So I'm assuming this is gamma. Do they say what is known as gamma? Just, I don't want to, tell you the wrong gamma. Where's gamma? Maybe they showed gamma. Where's gamma? Maybe here. Is there a gamma? Gamma. Which is gamma? Is gamma 1 over this, or is this gamma? Which is it? Okay, we don't know. So let's look it up. So let's just look up time dilation. I want to I want to be able to say things like everyone is used to hearing them. So time dilation, which is gamma. Okay, let's just ask them. Oh, you know what? Wikipedia maybe should have it. La 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 la. Oh, this is the past light cone. I thought this is a black hole. Oh, okay. Uh, where is gamma? I just need the definition. Simple inference. Observer address measure time. This is the thought experiment that should give you gamma, no? La 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 la. Time dilation. But what? Oh, there it is. So, yeah, gamma is 1 over. Okay. This is what we need. So, can they express it with gamma? So, which is it? So, gamma is 1 over. That means that T prime is always the moving observer, the moving whatever. So you can say observer. So oh, there it is. There's gamma. So gamma is 1 over. Right. Gamma is 1 over. So it's gamma the stationary. So T moving to T stationary is gamma. That's a definition, which is 1 over. Very confusing. Okay. La 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 la. Oh, Nicholas. No, don't. Don't what? Who's Nicholas? Who no don't and who's Nicholas? I don't know. What happened? To whatever a couple of minutes ago? Don't what? La 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 la. All right. So, um, okay. I was reading that guy's equations. I was reading that guy's whose guy's equations. That guy's who? Dialect? His equations are just these. And you can go watch, just look up dialect sound clock. Okay, this is all we need to know that T moving to T rest is gamma, and gamma is 1 over this. Okay, let's see what we did. Did we mess it up completely? Yeah. Oh, did we? I don't know. Let's go back to the previous one. This one, I guess. So what did we say here? Right. So I think it's 1. No, it's gamma. And gamma is 1 over this. So what are we getting wrong? So T moving is slower, meaning like 1/2. It's 1/2 over 1. So this is less than 1. So gamma should be less than 1 because time is slowing down in the moving, not time. Don't say time, say ticking. It's a ticking dilation. Don't say time dilation. If you say time dilation, you will confuse yourself. Say ticking dilation. There is no time dilation. There is ticking. Just ticking. Everything is mechanical. Because when you say time, it becomes this modern physics. Time is not the same. No, no, no. That's nonsense. Time is the same. Time doesn't exist. Time is an illusion. We're talking about a mechanical universe. In a mechanical universe, there's only clocks. There is no time. You can measure time using clocks, but there's only clocks. There's nothing else. If you stop saying time, you'll be fine. Start saying time, you're gonna get lost. I guarantee it. Because you start thinking, whose time? What time? Ticking, ticking, and ticking is measured. Tick every 2 seconds. Tick. Remember, the rule is remember you are dumb. As long as you remember you are dumb, you will do well. Because then you're not going to try and understand smart things. Because smart things don't exist. Only dumb things exist. This universe is mechanical. If you try to be smart, that means you're not being mechanical. If you're not being mechanical, you're wrong. The universe is mechanical. That's if the universe is not mechanical, then I don't know. Then fine, it's magical. It's look, this universe is either magical or mechanical. It's up to you to decide which. I go with a mechanical universe. I don't care for a magical universe. I don't know what that would mean. I don't know what that would entail, as the Discord people language say. All right. So this is less than 1. So gamma must be less than 1. That means this must be more than 1. But how could this be more than 1? This is 1 minus something. This must be less than 1. I don't get it. This is once every 2 seconds. Once every 2 seconds, this is once per second. What am I missing? Am I missing something? Oh, I'm not sharing the tab. Oh my god. Let's go back to this tab and see comments. Oh, we have comments. Blah blah blah. The guy you blocked. The guy I blocked. I don't want to read his comments. Why would I want to read his comments? Ticking. Yeah, ticking dilation. Exactly. Exactly. Yeah, good point. Exactly. Yeah. The smaller the clock, the slower it is. What do you mean smaller? The slower? What? And the more of them you can fit over volume, meaning more space, slower ticks. I don't know what you mean. So I don't know. I'm not there yet. I'm moving a little bit. So I'm still having a hard time figuring this out. What am I missing? Look, T prime, the moving must be ticking slower. We know that they tick slower. So ticking slower to ticking faster must be less than 1. Less than 1 meaning the denominator is bigger than 1. This must be bigger than 1. But how can it be bigger than 1 if this cannot be bigger than 1? This is 1 minus a positive value. This is less than 1. Then the square root must be less than 1. So this is bigger than 1, meaning, oh, the period. It's not the rate of the ticking, it's the period of the ticking. Oh my God, Jesus. Jesus Christ, la 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 la. Because we don't measure frequency, we measure periods. Okay. Let's see. I'm pretty dumb. I can't read and understand the equation. Well, that's good. Which equation? But look, I'm not going to have a discussion like this. You have the link. Join me. No, you don't. Let me give you the link to the Discord. Join me on Discord. Let's have a discussion. I'm not going to read. I'm sorry. It puts my brain to sleep. I'm so sorry. I cannot have a discussion with messages. Here's the link. Click the link. Join me on Discord. Ask me questions. I'd love to have a discussion. Otherwise, I can't. I can't. It kills my brain. I mean, yes. Okay. Oh my God. The powers mixed with the square root. Okay. I'll join. 1 second. Good. Come. Very good. Very good. Very good. Okay. Any hoo. So, I'm sorry for confusing everyone. Okay, so this is T. This is not T. T is not per second. T is second. So everything is upside down. So this is 2 seconds per tick. This is 2 seconds per tick. So let's take the 2 seconds, put here. You're here? No, you're not here. What's this? Wave hi. How are you? Join me. La 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 la. Okay, here is, we can put this here too. Here's the 2 seconds. Where's the tick? Here's the tick. 2 seconds per tick. This is 1 second per tick. Everything now makes more sense. Let's go to this. Okay. Are you gonna enter? You need to enter the general. You can see it on YouTube. You know where to enter. So click the general with the speaker. Not the general with the hashtag. The general with the speaker. La 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 la. Let me see. Are you having a hard time? Nicholas. Let me see. Hi. What's going on? Wait, are you human? Yes, I am human. Add friend. I don't know. Maybe you have issues. Maybe you're having um, technical audio issues. Anyway, so now everything should make a little bit more sense. All right. So the time 2 over 1 is 2. It's bigger than 1. So this is bigger than 1. So this is smaller than 1. Very good. So 1. Okay, now we can do this. All right. So we're saying the square root is equal to 1 over gamma. Okay. So the square root is 1 minus v squared over c squared. Okay. The next step is to square both sides. So let's square, right? Everything we do to one side, if we do also to the other side, we maintain the balance, right? You always remember this is algebra, which translates from Arabic al-jabbar. Like Allahu Akbar, Akbar is Akbar. And Gabbar just means strong. Allahu Akbar means the God of the moon is strong. Allah is not God. It's Allah. It's the God of the moon. Allah is Luna. That's why their symbol is the moon. Because the God of Muhammad was the God of the moon. Because they used to be idol worshippers. Now you know. Anyway, so this is Al-Gabbar. Al-Gabbar just means the strength, which means the balance. So you always remember that you're trying to balance on a fulcrum. You're balancing. So whatever you do to one side, if you do to the other, it should maintain the balance. It's geometry. It's a thought experiment. Algebra is a thought experiment. Okay. So you square this, you should also square that. Very nice. So now we can say that 1 minus v squared over c squared is equal to 1 over gamma squared. All right. So the next step is let's remove 1 from both sides. And let's multiply by -1 both sides. And now let's take the square root. Well, let's multiply by c squared both sides. And now let's take the square root of both sides. And that's v. That's v given gamma and c. That's incredible. We can deduce the actual velocity There's no question, there's no uncertainty about this. Assuming a constant velocity, there's no uncertainty about this. We know the velocity of the observed moving boat, moving clock. This is unbelievable. The last thing I expected to be able to do is directly from a thought experiment deduce the other guy's velocity. Oh my god, this is just incredible. All right, so his velocity is the square root of, of this thing of 1 minus 1 over gamma times c, because of c squared times c. So it's c times that gamma squared. Don't forget. So it's 1 minus 1 over gamma squared times c, because c comes out of the square root. Absolutely incredible. Wow. Didn't think we would get this far. Wow. Because yesterday I was staring at a piece of paper and I had no idea how am I ever going to figure this out. But slowly, I'm beginning, right? I'm dumbing down. I'm saying, what exactly do I know? What exactly do I not know? And this is now exactly what I know. So we can start over. So what did we have? Right? This is his velocity given gamma. And gamma is just t prime over t, the time of his period that I am able to get, because his t prime, by the time it gets to me, it's still t prime. It doesn't change. I see his period just as he sees it, assuming no Doppler shift. And even if there is a Doppler shift, I can calculate the Doppler shift because of the angle. Can I? Let's ignore for now the Doppler shift, right? Let's go through the simplest case. Wow, what an accomplishment. Oh my God, this is such an accomplishment. So this is gamma. So let's say 2 seconds over 1 is 2 seconds. Yeah. Are you finally able? Whiteboard. What is this? You've been invited to join. No. You need to fix your audio, Nicholas. Fix your audio and join me and then you can join. You have to enter the general. This is called the general VC, the general voice chat. You have to click it. If you don't know how to enter, to ask me. You need to click it. If you're on the phone, I mean, yeah, you haven't seen me entering and leaving. Anyway, you need to enter the general voice chat. Then I'll see you here, and then I'll be able to talk to you. Let me just make sure everything is on. Let's just make sure the audio is okay. La, 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 la. Very good. Yeah, everything sounds terrific. Okay. You have to go through authentication. Yeah. Okay, but ask me. But you seem to have been able to join Discord. So why are you unable to join the general VC? So that's your next challenge. Anyway, so given gamma is equal to 2, so 2 squared is 4. 1 over 4 is 1/4. 1 minus 1/4 is 3/4. The square root of 3/4 is the square root of 3 over 2 times c. That is his v. So v is equal the square root of 3 over, I think, 2 times c. The square root of 3, right? It's less than 4. It's less than the square root of 4. So this is less than 1. But he's actually moving really fast because he has 50% time dilation. That is very fast. Amazing. Everything fits together in the kitchen sink. This isn't the kitchen sink. This is time dilation in the kitchen sink. Okay, so we know we definitely can figure out the velocity. The next question is, what does he, okay, the same as we were able to measure C, let's now have him measure C. Let's start over. Let's start over with the thought experiment. I just want to make sure everyone is following and I am getting it right. So start over in the bathtub. In the bathtub or kitchen sink, all the same. La 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 la. Anyone knows the song I'm singing? What is going on with you, man? Why are you having such a hard time? Tell me, at least update me why you're unable to talk. And why are you texting here? I don't get message when you text me on YouTube on the chat. There's no notification. I don't get any notification. If you want answers, text me here. Text me here. This is the best place to text me. Right here or in the private DMs, doesn't matter. Text me here. Text me here. What's the question? For now, I'll answer here. It keeps saying I need to claim my account before I can enter general. LOL. Keep going. I have authentication errors. Okay. It is making me authenticate everything. Haha. I'm almost done. Yeah. I know. And you can lose your authentications. I've lost my account. I've already had a server before, had many friends, and made an authentication error and got blocked out of my account. They're very sensitive and, of course, zero help desk. But please don't text me here anymore. Please do me a favor because I'm not going to see it and I don't want to come back and check every 2 seconds. So on Discord, I get a notification. But so please notify me on Discord. Very nice. Okay, so let's start over. It's really very straightforward. So, what do we have? We have a finite bathtub. There is the bathtub. Very nice bathtub. Oh, Nicholas. Nicholas, how are you?
Hey, how's it going?
Terrific.
Oh, there's a delay.
There's a
Hello.
delay. Hi, Andrew. Both
Oh,
of you are coming at the same time, of course, because that's how the universe works. What's up, Nicholas?
hey, what's up? How you guys doing?
I'm okay. So, do you have
I'm
any
doing great. What
questions?
about you, fam?
So I'm trying to figure this thing out. So where my brain gets like messed up is like the one over the one over is like an inverse proportionality, but like the square root over the velocity squared over the c squared, like I get mixed up with square roots and power scaling when they're
Wow.
like that. I have to have them separate somehow. I think it's just I don't know.
Okay, so
Maybe.
in order to understand gamma, you have to watch
Mhm.
dialect sound clock slowly. They go very slowly, and you have to stop the video. I did a review of it. I mean, that's how I learned it as I was watching it because I didn't know gamma. I think yesterday or 2 days ago or 3 days. I don't remember. So I had to learn how to develop gamma. So it's really
And this
What
is
type
for like
gamma?
a moving mass observer, right?
it doesn't matter that right now we're not considering mass. There's you could say there's a moving clock, and we're just trying to figure out
Well, the
here.
wait, the clocks are made out of mass, and so it's
No,
for the
no,
mass observer, right?
no. These are for now. Everything is massless. We're not doing mass yet. So
Okay.
the thought experiment goes like this. So I am an observer over here, and all I have
Mhm.
I can only detect waves. I have a wave detector, and you can think of it as one of those rolling pads with a needle, and I can just see the waves. Either there is waves or there is no waves. That's all I know. It's waving. It's not waving. That's all. That's all. That's the only input I have.
So like if you have like a wave bouncing in between like two like plates or whatever, but then you move the plates like in a direction really
Right.
fast.
Okay.
Okay, got you.
Okay. So right.
Yeah.
The next step is that there is a boat here. Wait, Andrew, please stop. Andrew, no, no,
All right.
no. I don't want to. Andrew, I don't want to kick you out of the room. You're getting in the way. You can draw somewhere else. You don't have to draw at the center. I need this space.
Yeah. Right.
I need the space so you can draw somewhere else. Stop, Andrew. Andrew, you gotta behave. All right.
Oh.
So, all right. Okay. So what's given? Okay. So the next thing is that there's a boat here. Andrew, can you stop? It's
And this
like
is
True.
you're talking about light cones, right? Like you get a
no,
forward
no,
and a
no, no,
backward.
no, no. I don't know
Backward.
I don't know. We have a bathtub. We're starting from scratch.
Okay.
We're in the bathtub. This is a top view of the bathtub. This is my
Okay.
wave detector. That's all I have. I don't even have eyes. It's dark. So all I have is I can just sense waves. That's all.
Mhm.
Now this is very similar to
Right. You feel the inertial force, right? Like the resistance.
no. There's no force. There's no force. No force. No
Okay.
inertia. Nothing.
Okay.
So all I have. This is a top view of a bathtub filled with water, and I have a wave detector, and it can just detect waves, and this is where it's written. So here's waves. This was no wave. Okay, now there is an object here, like a boat or a rubber ducky in the bathtub,
Uh-huh.
and I
Hmm.
wanna discover its velocity if it has any velocity. I want to discover its velocity, but I'll tell you what's given. Given,
So you would do the 1 over square root of velocity squared over c squared to get that?
well, I don't know. I mean, I'm okay. So tell me what you suggest. So I want to discover its velocity, but right now there's no input. I didn't tell you what input.
Oh, yeah,
I
you want to determine its delta velocity, right? Like that's
There's no delta.
I'm
Delta
still trying to
delta means change. There's no.
yeah, change in the velocity.
So no, there is no. So we're assuming that change in velocity is equal to zero, and this is called
Okay.
an inertial frame of reference. So
Got you.
nothing in this experiment is changing velocity,
Got you.
and
So it's no
mhm.
acceleration.
It's what
There's no acceleration.
exactly? Delta v zero,
Got you.
acceleration equals zero. Exactly.
So this is for relative comparisons between different reference frames that are moving, right? Am I right? In
Well,
terms of space time trade off, right?
you're going too fast. I This is much
Okay.
simpler. Much simpler. This is a bathtub,
Okay.
and we
Got you.
have a wave detector,
Hmm.
and there might be a rubber ducky here. We don't know, and it might be moving. We don't know. That's it. So if it is there and it is moving, it's moving at a constant speed, and we want to
Right.
discover what that speed is if it's moving. But right now there is
Oh, okay.
no
Got
there's
you.
no we're not getting at this point we're not getting any information. So what information do we need? So if we're not sensing any waves, then I'm assuming there's no rubber ducky. But let's
Right. So
assume that
you
this
would have to like
go ahead.
oh, I guess you would have to like triangulate it from somebody else, like if you could see somebody else, right?
But right now we didn't say that the rubber ducky is transmitting any wave. So first we need to say
Oh,
that
okay.
we need to assume, or we need to, right, this rubber ducky has to convey information. This is akin
Hmm.
to in real life that we see. Seeing
Yeah.
is a light wave. We see waves.
Yes.
So this is
Yes.
akin to that, right? So this thought experiment, if we could figure out how to make this work in the bathtub with a rubber ducky and a wave detector, then we have figured out relativity, Einstein's special
Yes.
relativity.
That's right. That's
Right,
exactly right.
right. So let's, so, okay, so
It's
uh,
like a V that trails you.
what's a
Well,
V?
well, I guess that. Well, the V is like what trails you, right? And that's like what's being communicated to the detector
I,
is the wave, right?
draw. You can draw on this whiteboard and show me what you think. I don't know what you're saying.
Yeah, yeah. Oh, where is that? Okay, there we go. Yeah, let's do that. Okay. Um,
You have to
keep
scroll in,
scrolling.
scroll out. You have to play with the
There
scrolling with your mouse. Are you using a laptop
we go.
or an iPhone?
So we got the. Let's see here. I'm using a computer. Let's see
Okay,
here.
so you need
So
to.
we got that guy here, and then
I'm
we
not
got the
seeing.
waves going
Not.
back this way,
I'm
and
not
this
seeing.
guy's going this way.
I'm not seeing your pointer.
Oh, share. Got you.
No,
So
not
that guy
share.
is moving
No,
forward.
no, 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 no. You need to draw on my
Did it work?
drawing. Are you watching my drawing?
Oh, I see. Okay, let me try that. Um, let's do that.
You have to open the
Share that.
right drawing. It's called start over in, I guess, the
Yeah.
bathtub.
Okay. So you got the guy here,
No,
and then you got.
can't see you. I cannot see you.
Oh, I gotta share it, right?
No, you don't share. You just need to open the right image. It's called start over. It's the last one.
Oh, it's the last one. Okay.
Yeah.
Um.
It
So
starts
it
with
says
the
start
word.
over in the
Yeah,
bathtub,
exactly.
and then when I go to that,
You know.
it's just a blank page.
So scroll out. You have to scroll out, scroll out,
Oh, I
scroll
see.
out.
Okay.
Yeah. Yeah, it's
My
weird.
mouse feels screwed up.
La 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 la. You got to continue scrolling out until you see the
One
full
second.
page.
My mouse wheel screwed up. Let me try to control
Scroll
shift or
out.
something.
Scroll out means you gotta roll the roller. You have to roll it towards you. Roll the
Yeah, one second.
finger towards you. That's scrolling out,
Okay, I'm
isn't
here.
it? No, I still
My
can't see
scroll
you.
wheel is broken, but I'm here.
No,
So
I
okay, where do
can't.
you want me to draw this thing at?
I can't see your.
I was,
I can't see your
okay, so
pointer.
here we go. So you got. Hold on, let me try that again. So you got this guy here.
No,
He's up here,
no, I
and
cannot
then
see
there's
your
the.
pointer. I cannot
Let me
see
back
your
out of that.
pointer.
Okay, I gotta share it. That's why.
No, no, you
Gotta
don't have to share.
go
No,
here,
you don't
here,
share. No, no,
share it.
no, you don't
Well,
share.
I don't share it.
No, you don't share.
Okay.
Like no one
Why
share.
can't I share
I
it?
don't share. You don't share. It's auto. It's auto. The sharing is implicit. You just have to scroll
Uh,
out. Have you scrolled out?
yeah, I scrolled out.
So do you see
So
the
like,
entire image?
yeah, I see the image. You got a box here, and it says V equals 2, I think, and then you got like a um
Here.
delta V equals 0.
What letter did I just draw in a box?
Oh, an M in a box.
Okay, but are you seeing this on YouTube or are you seeing this in Discord?
No, I'm seeing this in Discord. I'm drawing on here. You don't see it?
No, I don't see
Let
your
me look on. Let
house.
me look on. Oh wow. Okay, so I see. I'm gonna have to go to the box. Let's see here. Uh, so
I
here
don't
we
see your
go. We got
pointer.
this.
Oh,
Do you see
finally.
that?
Yeah, but it's weird that
So
I don't see your pointer. So I see you drawing without a pointer. That usually I've never seen. I've never seen that. So I can't see your pointer. You're something. So just refresh Discord, refresh Discord, or even you might even
okay,
have to leave and come back. Try
okay,
refreshing, and if that doesn't work, leave and come back. Like you're gonna exit the room and come back. Tell me that
gotcha.
you refreshed. Mhm. Oh, you're leaving and coming back. Okay. La 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 la. All
Here,
right.
let's try this.
Yeah, try it again. Yeah, Discord has a bunch of bugs. Leaving and re-entering usually resolves the issues. Oh my god. La
Okay,
la
so I'm gonna zoom
la
out.
la. Zoom out, yes.
Controller plus.
La 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 la. La 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 la. Are you managing to zoom out?
Yep. Okay, so I'm zoomed out. Okay, so do you see my little
No,
circle here? So that's my ducky.
no.
You
Try,
don't see it?
no. Can you try and draw something over the M? Where it says M, can you draw?
Oh, over the M. Hmm. So I can move the M around, right?
Yeah, I
Did I move
cannot.
it?
Yeah, but I cannot see your.
Okay,
I
let me
cannot
try
see your
this.
pointer. Try drawing. Yeah, I cannot see your pointer. Really strange. Let me try. I'll leave and come back. Give me a second. Maybe I'm.
Okay.
Let me leave the room. I think it will be fine. Join. Let's see. La 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 la. Oh, let me. Okay, I see yours. I see your pointer now. I was the cause of the issue. La 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 la.
So
Okay,
this is what I'm like. So here's the like the water in here, and then this
what are
is
you?
the.
But what are you drawing? I'm not following. What's your question?
Oh, you said okay. So say we have a detector over here, and
No,
then the duck right.
no. I don't know what you're drawing. So let's
Oh,
clean up a little bit because this was just for you. Okay,
okay.
so I'll tell you the story. The story is that there is there is this is the detector.
Okay.
This is my detector and it detects waves. That's all I have. I'm blind, it's
Gotcha.
dark, I don't see anything. All I can do is detect waves. That's it.
Okay.
That's step one. Step two is there might be a rubber ducky here. It might be moving at velocity v. And if it is, I'd like to know what the velocity is. Velocity just means speed. That's it.
Okay.
Now,
Got you.
for now, it's not sending, it's not bobbing, it's not sending any information. It's not, and the only way of information, the only means of information is waves. So for now, it's
Got it.
not bobbing, it's not transmitting anything. So as long as there's no transmission, I have to assume there's no rubber ducky.
Right. Right. Got you.
However, I know about the rubber ducky because I bought it and I know how it works. I know that the rubber ducky is always ticking. It's always ticking. And I measured its ticking when it was stationary next to me. I measured its ticking at one
Hmm.
tick per second. Every
Okay.
second it ticks. Now, what is a tick? So a tick
So
is
it's just like a detection,
almost.
like
It's a,
something smacked you or
eh,
something like that.
it's okay. So this comes out of Einstein's thought experiment. Einstein came up with this clock. So the ticking is a clock that has two sides. So when you turn the ducky on, immediately it makes a wave, and this wave reaches the other side where there is a detector. When the
Hmm.
detector detects a wave, it sends a wave back. And again,
Got you.
when the first side detects an incoming wave, it sends another wave back. And this continues. So
Hmm.
this is the rubber ducky. The rubber ducky is always ticking. And we know
It's a
that
clock.
it's a clock, but it's a wave clock. It's a water wave clock. Now
Got you.
you
Got
can
you.
go to the store and you can buy this ducky, but no one is producing them. So I already offered anyone who's listening, please produce this rubber ducky because then you can conduct experiments with special relativity in your bathtub. You can teach your baby special relativity with a
Hmm.
rubber ducky that works like this. Now, this rubber
Yep.
ducky, when it's stationary, it's ticking once per second. Okay.
Got you. Got you.
So it's tick tock, that's 1 second. Tick tock, 1 second. Okay. Now this rubber ducky, let's move it. This is a stationary rubber ducky. What would a moving rubber ducky look like? So maybe we should okay,
Like this,
let's right. Exactly. Exactly.
and that's longer distance, right?
Exactly. It's longer distance, so it's gonna wave because it's a wave, unlike Einstein. Wait, why can't I draw? Okay. So it's a wave. So Einstein's thought experiment, I think, is broken because he uses a photon ping pong, and he says it's always moving at the speed of light. That's nonsensical. That doesn't make any sense. So
Yeah, that doesn't make sense.
right. In my thought experiment, it's a rubber ducky that ticks that uses waves. So a wave is actually, well, in water surface is two-dimensional. So when it ticks, there's waves coming out until they hit the other side. And if it's moving, then it's going to hit, right? But by the time, so let me draw this. Follow me. Follow me. I'm scrolling down. Let's get rid of this. So let's draw again. Just try. Okay. So here is the bathtub, and here is the clock. So the clock it ticked here, and the wave. But let's say by the time it reaches the other side, the clock is already here. That means these waves really have to travel a much longer distance, taking up much more time until they hit. Could you just maybe stay out of my way? I'm having a hard time when you're right over
My
my
bad. My bad.
yeah. So right, and that's the angle that you drew, but that's because
Hmm.
this is right. This is the clock
Yeah.
in position one or time one. This is the clock during T2. And again, we're going to have the clock again. Could you just move out of my way, please?
Oh,
Could you move? Thank you. And this is T3. And again, it's going to wave. It's going to wave in all directions. It doesn't know. When it ticks, it waves in all directions. It doesn't know where the detector is. And that's the problem. That's the other problem with Einstein's thought experiment, that his ping pong is a genius. He knows the future. The ping pong always knows to bounce to the right to the proper place. Makes zero sense. Anyway, so again, it's going to take a long distance, longer than the original stationary tick tocking.
Mm-hmm.
So a moving clock is tick tocking, is ticking slower. Now this has nothing to do with the passage of time. So that's another
Gotcha.
issue with Einstein and everyone interpreting relativity. It has nothing to do with time. Like this is a bathtub. No one is going to tell me that
Right, right.
time has changed in my bathtub. That is
Oh no, it has. No, it really has. Because the gravity field, once the wave hits the gravity field, the um the wavelength decreases and the speed will decrease as you hit the boundary of whatever is creating the, you know, so the time will actually the clock will tick slower, but it'll have a higher frequency and momentum.
okay. We're ignoring gravity. I don't know what you were just talking about. So no one
Yeah,
is
so
gonna.
think of a bunch of little clocks like this. Like, so you have a bunch of little clocks
No,
and say here's your mass right
no,
here,
no, no, no,
right?
no,
Yeah,
no,
yeah, yeah.
no,
Try this, try this.
no, no,
So,
no, no,
and
no,
your wave is moving.
no, no, no.
Well, how do
Well,
I
that's
just
that's not
create?
where that's not
Hold
what
on.
I'm trying to accomplish. I don't know where you're going. I have. I'm
No,
trying.
no, it's better. It's better. Trust me. Check this out.
No, no, no,
So I'm gonna.
no, no, no. We're not doing that. We're not doing that. We're doing something else. I'm trying to show Einstein's postulate. I'm trying to show
Gotcha.
we can derive. Please stop, 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 stop. Can you stop?
Okay, okay, okay. Go ahead. Go ahead.
We're trying to derive Einstein's postulate. Einstein assumed his postulate. I want to be able to derive it in a bathtub.
Hmm.
And if we can do
Gotcha.
that, then we have that's an accomplishment. Then we have
Hmm.
other things we want to accomplish.
Yeah,
Let me just clear this up. So
but you got to also realize the bathtub, it has curvatures in it, so the water is not really like, flat like that. So you'll have waves on it, right?
no, no,
And
no, 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 no. We're not doing that. We're assuming in our bathtub. This is an experiment we're conducting actually in our minds, but you can do it in your
Mhm.
kitchen sink or in your bathtub. As far as you can tell, your bathtub is flat, and I don't know what else you want to say. So, assuming
Oh well, like, so what I mean is, like, in the universe, it's not really like a bathtub. It is
no,
kind of like a
no, no,
liquid,
no, no,
but
no,
but
no, no,
okay.
we're not doing that. We're not. We are trying to derive Einstein's postulate of the moving observer we want to show is measuring the speed of the waves just like
Hmm.
a stationary observer measures the speed of the waves. We have something very
Hmm.
specific we want to demonstrate. So
Okay,
we need to be focused on that. All right.
gotcha,
So
gotcha.
now what I was saying is this has nothing to do with time. No one is going to tell
Hmm.
me that in my bathtub time is time is moving slower. That's an unscientific statement to claim that
Oh no, 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 no! It's a scientific statement because like when you get to the edge of a black hole,
no, no, we're
like,
not doing that. We're not doing that. Look, you got to stop. You got to
okay.
stop. We're doing something very specific. You got to like you're wasting
Hmm.
my time. I'm not doing that. I'm not doing like I've done lectures about that. I've said everything I have to say basically about those
Hmm.
things. I'm trying to do something else now. I'm trying to
Gotcha, gotcha.
derive Einstein's postulate, the speed of the medium of waves in a medium is
Hmm.
observed to be a constant by all moving
Mass observers,
observers.
mass observers. Yeah,
No,
but mass
no, there's no
radiates
mass.
gravitational
No
radiation.
mass. Stop. Okay, look, I don't know what you're trying to do.
Hold on. No, no, no. There's
Okay, I'm gonna
factors you're missing, bro.
look.
There's a whole array of factors that you're missing.
Okay, I'm gonna have
So
to.
like,
Okay, I'm gonna have to block
oh my,
you.
that's fine. That's fine. My bad.
You want me to block you?
No, no, no. You're fine.
I think you're trolling. I don't think you're serious.
No, I'm not. I'm really serious. Trust me, I'm
Then
serious.
you gotta stop.
Okay.
We're doing special relativity. There's no
Okay.
mass. There's no acceleration. There's no curvature. There's no black holes. There's nothing.
Got you. Got you.
Really, very,
So it's just flat.
yes.
Got you.
Okay, so again, no one is going to tell me that time is moving differently relative to moving observers.
Exactly.
A moving rubber ducky is not experiencing a different time. You could say that the toy rubber ducky is going to tick slower
Mm-hmm.
if it moves relative to the medium.
Right. Right. That's true because it's flat and it's the same
I
like
don't know.
granularity everywhere.
I have no
Because
idea.
you have water molecules, right? So the kinetic energy transfers
No,
reliably
no, no,
because
no,
all the water
no, no,
molecules are the
no,
same. It's the
no.
same density.
I'm going to block you.
My bad. My bad. Go ahead. Go ahead.
All right. Um, how can I? Let's put him on timeout. All right. So let's continue. Um, all right. So, okay. So let's start over. Let's create a new thingy. Take two. La 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 la. La 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 la. All right, so let's start over. So we have a bathtub, and we said we have a rubber ducky that is ticking. We know it to be ticking once every second. Okay. And we have a wave sensor here. And every time it ticks, we get a signal coming. So we know, so we hear those ticks. And because it's moving, we know, oh, if it's moving, its ticks will be slower. So we're going to get as input, as data, we're going to discover T prime. And let's say T prime we measure to be once every one tick every 2 seconds. That's given. So we know that the rubber ducky is experiencing tick dilation. There is no time dilation. It's experiencing a tick dilation. We know that our ticking is once per second. That's our ticking. What else? So this guy, I gave him a 60-second timeout, but he never came back. Or maybe because he's blocked. I'll remove his block if he wants to come back. Unblock. Welcome to come back. But if he misbehaves again, I'll put him in longer and
Back.
longer. You'll get a longer timeout if you continue. Like, if you
Got you. Got you.
look, if you're having a good time and you want to make fun of what I'm doing, then I don't have time for nonsense.
No, I don't want to make fun of what you're doing. I was just trying to like see this other like larger perspective of it.
If you continue looking for larger perspectives, you'll get larger timeouts.
Got you. Got you.
Yeah, I'm sure you got me. Got me. All right. So we know this is given. So his ticking is given. My ticking is given. So what can I deduce? Therefore, is his velocity. So incredibly enough, from this I can deduce his velocity because he's
Mm-hmm.
actually experiencing a massive tick dilation relative to me.
Mm-hmm.
His clock is ticking basically at 50%. So he's experiencing
Mhm.
50% ticking dilation. Okay, so we know, so what do we know? We know that T prime to T is gamma. That
Mhm.
we know. We also know that gamma is equal to 1 over the square root of 1 minus V over C squared. And this is derived from a thought experiment.
Mhm.
Just please stay out of my way. Move your pointer. If you I'm gonna time you out
I'm up
every
here.
time you misbehave.
I'm out of the way. I'm
No, no.
I'm
You're
out of
gonna
the way.
get a timeout, this time 5 minutes. All right. So uh okay, so we know T prime over T is gamma, and we know gamma is this. Let me just check the audio. Let me check the audio. La 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 la. Yeah, the audio is supposed to be very good. Well, it's been, a couple of days since we had an issue with the audio. All right. So the next step, okay, so we know gamma, and we know C. We can measure C, and we're assuming C is a constant, meaning anywhere we measure C, any stationary measurement of C is a constant. We're assuming that it's water, and water doesn't stretch and doesn't bend, doesn't do the nonsense that Einstein claimed in general relativity um, that space does. Okay, so let's say given C is 1 meters per second, which is pretty. I think it's pretty correct. It's right about there, right? A water wave moves at about a meter per second or something. Anyway, very nice. We know, right? What do we know? We know gamma, because gamma, we know T prime and we know T, so we know C. So all we don't know is V. So we can deduce V. So what is V? Knowing gamma. So we went through the math. So we're gonna multiply both sides by this square root. So the square root is equal to 1 over gamma, and the square root is 1 minus V over C squared. Then we take the square root of both sides. So not the square root, with the square. We square both sides, we get this. Then we subtract 1 from both sides. Then we multiply by -1 both sides. Then we take the square root of both sides. And then we multiply by C. So this is times C, both sides. And that's going to be V. So V is going to be, this is incredible. This is 1 minus 1 over gamma squared square root C. Unbelievable. Now we know everything. We know gamma. Gamma, let's say this. So his ticking is 2 seconds per tick and 1 second per tick. So this is going to be 2. So gamma is 2. So assuming gamma is 2 and C is 1. So 2 squared is 4. So this is 1/4. 1 minus a quarter is 3/4. So this is radical 3. It's just radical 3 over 2, which is less than 1. times c in this case, which is uh, it's a very it's like it's very fast. So that's the example. So if c is 1 meter per second, this is almost 1 meter per second. How much is it? What is radical? Radical 3 is between radical 2 and radical 4. It's, let's say it's 1.5, I guess. So this is I don't know, 75% of 1 meter. So it's 0.75 meters per second. So this ducky is moving a little slower than the waves. So you can imagine a duck, a rubber ducky. So this rubber ducky has a built-in engine, like zzz, and it's moving. As it's moving, it's making waves, but and it's almost moving at the speed of the waves. It's almost catching up with the waves that it's making. However, and here is the big however, we want to claim that this rubber ducky will measure the speed of the waves moving away from it as c. We claim, right, first of all, we don't know. We're saying, okay, the rubber ducky is going to measure the speed of the waves moving away from it at some c prime. What is c prime? That's the question we need to answer. What is c prime? What is the rubber ducky measuring these waves moving away from it at? That's a good question. How do we do that? Mhm. Well, the question is, how did we measure c to begin with? So we took a distance like 1 meter, and we took our timer, which is our ticking. We are also a ticking ducky. So everything is symmetric in this story. So we are a ducky, a rubber ducky, just like the rubber ducky that we're observing. And actually, that rubber ducky is observing us. But we'll get back to that. This is incredible. We're building a theory of relativity that is actually one step, multiple, I'd say 2 steps more advanced than Einstein. One is because we're doing everything with water in a bathtub, and the other is we're proving his postulate. What he assumed, we're proving. And this will prove this is terrific. This is the ether. This is the, I think, the best proof for ether. But more important than anything, we're going to remove Einstein's postulate, his famous postulate. No one knows where he got it from. I don't know where he got it from. I don't think he knew where he's getting it from. I don't know where he was getting it from. This notion, because he said he didn't get it from Michelson. So I don't know where he got it from. So it makes what he did completely unscientific. Okay. Okay, so this guy invested so much time just in order to, like, to joke, to troll. Really strange. People are really strange, you know? People are really, really strange. Okay, let's continue. hmm The next step is going to be, let me think about it. Well, we got this far. It's not too bad. So the next question is, how did we measure the speed of the waves? How did we do that? How did we do that? Let me check. Messages here, messages there. Oh my God. Terrible, terrible news. Everything is filled with terrible news. Okay. Yeah, where the world is ending. This could be This could be the end of the end, or the beginning of the end between what's happening in Russia and what's happening in the Middle East. We're in trouble. Let me refill my water. Okay, so how did we measure how did we measure the speed of the wave? So I have to assume that we took a meter and we took our ticking rubber ducky, and we let it tick. We don't know any better. We might ourselves be moving. We actually don't know that. But as far as we know, our ticking is once per second. And over this 1 second, we measured 1 meter, we measured waves to travel across this 1 meter at 1 second. So we came to the conclusion that C is equal to 1. That's our conclusion. And we have to conclude because we see that we are stationary. We don't know, right? This could be in the dark. We just don't know. This rubber ducky cannot know. The ticking is the ticking. This is its consciousness. This is something that that's like the second postulate from Einstein that all physics experiments. There's no physical experiment an inertial observer can perform that can tell them anything about anything about their motion. Motion is right. That we know that's incorrect because we don't know that, but with an interferometer, we should be able to detect motion relative to the medium. The rubber ducky can certainly detect. The rubber ducky can certainly use an interferometer, a water-based interferometer, a wave emitter, a wave splitter, a mirror, a mirror, and a detector. And then this should rotate, and an interference pattern should come out of it, right? So a rubber ducky. So this is a pretty much state of the art rubber ducky. It has a wave detector, it has a ticking clock, it has an interferometer. It's not a simple rubber ducky. It's not such a simple rubber ducky. Not as simple as Don't let a rubber ducky fool you. This is it's an expensive rubber ducky, but if you mass produce it, you should be able to get the price to something affordable. All right. So mhm. So that's what we did. So I have to assume that's what they did. That's what right. So a rubber ducky has to have an internal length, and it has to beat internally. It has to tick internally and figure out the speed of a wave. So every rubber ducky tells us its detected speed. The question is, we know that this guy is moving. What do we know? What is it measuring as the speed of the wave? So every rubber ducky has an internal length. It ticks on this side. Basically, this is one tick. So every time a rubber ducky talks, so every tick the rubber ducky knows the length, and the time is a tick. The tick is always a tick, and the length is always the length. Therefore, the speed must be constant. This actually, we don't need anything. That's it. That's it. Wait, but what happens if the ducky moves very fast, very, very close to the speed of c? Okay, so it's going to tick. It's going to take a very, 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 very long time, but it's always going to tick. It's always going to cross this distance at one tick. So that's it. We don't need anything else. That's the proof. We actually don't need gamma. We don't need time dilation, length contraction. We don't need anything. 1 second. That's the proof. We actually don't need anything. The speed of the medium, the speed of waves in a medium is always one tick of the internal rubber ducky, one internal tick, one clock tick. If that's how it's calibrated, it's always going to be the same. Done. It's trivial. It's trivial. No one has ever thought of this? I don't believe it. So that's the proof. It's by far simpler than I could ever expect. I never expected this postulate to be proved so easily. I thought we would need to divide and this and gamma, shmamma, bamma. No, there's nothing. There's nothing. There's absolutely nothing. It's always going to be a single tick. If it's a single tick, when it's not moving, it's going to be always a single tick. And if it's traveling faster than c, then it still will be a single tick. It's just it will never reach the other side. But if it ever slows down to below c, it will go back to, it's always the same speed. So all observers are always measuring c as the same number, meaning for a given distance, once we made it internal, I mean, it's not really internal. I mean, water is flowing through the rubber ducky. Water is flowing, and it doesn't matter. Water is flowing. It doesn't matter if it's ticking this way or that way. It could be ticking up and down. And as the rubber ducky is moving faster and faster, let's say this is 1 centimeter. So it's measuring, let's say it's usually 1 second per centimeter. Let's pretend that. So it doesn't matter if the rubber ducky is moving at an incredible velocity, close to c, very close to c. So it's going to take a very, very, very long time for the wave to get across. Okay, but it's always going to be one tick. That is the definition of a tick. It's always going to be exactly one tick because that's the definition of a tick. So it's always going to be that distance divided the same distance by the same time. Time, it's not time. Don't say time. There is no time. There's only tick. Where we live in a mechanical universe. We don't know what time is. We can only measure time, or we know what time is, right? In science, you could say we don't know what something is. We can just measure it. Something is what it is measured to be. So time, we measure time through ticking. So that's time. That's the proof. Einstein's postulate is trivially evident. Once you once you assume a rubber ducky, a ticking rubber ducky, it doesn't matter which direction it's ticking. It doesn't matter where it could be ticking diagonally. It doesn't matter. The ticking will slow down relative to a moving or non-moving, relative to a stationary. It doesn't matter. Relative to somebody else in another frame of reference, it's ticking slower or whatever. It's always going to be ticking slower, I guess. But it doesn't matter because it's always, as far as the ducky is concerned, it's always going to be ticking one tick per 1 unit of distance. So the speed of the wave per every inertial observer is a constant. We don't need Einstein's postulate. Okay, we gotta look this up. There's no way no one has ever thought of this. So, proof that, here, let me, yeah, I'm sharing. Okay, so proof that, oh, so if I look here, you can see it. Maybe this you can see. So, proof that what? Enable search suggestions. Oh, enable? Prove that Jesus existed. Okay, finally we can. I didn't know we can enable it. Proof that what? That the speed of. Yeah, proof that the speed of light is constant. It's not the speed of light, it's the speed of any. The speed of light is a fundamental constant in physics, and its constancy has been extensively demonstrated. Yeah, it does. That just suggests that suggests the ether. That's a suggestion that there is a medium through various experiments and theoretical frameworks. Oh, there is a theoretical framework. Here are some key. Okay, Michelson Morley, that's useless. Einstein's theory, no, he just postulated. Experimental, no, I want theoretical proof. Theoretical framework. A constancy of the speed of light is also a fundamental aspect of modern theories. No. Quantum, no. General, no. Current understanding, the speed of light is now recognized as a fundamental constant of nature. No. The fact that it's constant, the fact that it's constant for all inertial, okay, let's change it. Proof that the speed of light is constant in all inertial frames of reference. That's the question that I'm asking. Prove that the speed of light is constant in all inertial frames of reference. The speed of light is derived from Maxwell. That's not what I'm looking. I want the proof in a bathtub. As a consequence of the invariance of physical laws. Nope, that's a postulate. The speed of light must be the same. Nope. Illustrations. I don't care. No. According to special. No. Both of no. Principle of equivalence. In a non-inertial frames such as those affected by gravity, okay, the speed of light may appear to vary. However, I don't care. Principle of equivalence. No, I don't think so. Shows the speed of light remains no. Conclusion. No, no, no. Someone must have done this. I can't be the first person to notice this. Why is the speed of light considered a constant? In all, photons move through local space they exist in. Photons do not move based on an observer's perception. It is ironic that of Einstein's two postulates, the first postulate states there is no absolute space, but the second postulate states the speed. Yeah, that's maybe they discuss it. Why is light speed constant in all reference frames? Hey, this is my first post. I'm a biology major. I know pretty much nothing about physics, yet sometimes it interests me way more chromosomes do. So, given that I know nothing about physics, this is probably, oh my god, inertial frames of reference. Practical terms, the equivalence of inertial reference frames means that scientists within a box. Is anyone watching? No one is watching. So no one knows. We just figured it out. Wow. The scientist within a box moving with a constant absolute velocity cannot determine this velocity by any experiment. That's incorrect. Otherwise, the difference would set up absolute standard. Well, then we should prove that with an interferometer. We know how to do that. Why is the speed of light constant? If you make some basic assumptions about symmetries, there is really only two possible options. There exists a speed that is constant in all inertial reference frames and all masses. No, you don't need, if you make some basic, you don't need to make that assumption. Special relativity, why the speed of light in a vacuum is the same in all. Okay, that the speed of light is fixed constant in all inertial frames is consequence of Maxwell's equations. Is it? No, it assumes. Yeah, but we don't need to say that. This is electromagnet. It doesn't need to. It's in every waving framework. This is wave mechanics. Gravity. No. What is the fundamental reason the speed of light being a constant? In classical sense, all waves have the property that their speed is constant in any given medium, because the speed depends only on the properties of that medium. Okay. So are you saying there is a medium? I need to understand. Is there a medium? If there is a medium, fine. But I understand there is no medium, so you got to make up your mind. What is the blah? I presume your question refers to the vacuum speed of light, and lest we forget, the speed of light is really just a conversion factor that allows us to replace unit of length with units of time, or vice versa. So why this conversion factor the same everywhere? Bear with me, but I need to show a little bit of math. In general relativity, we often talk about the so-called element infinitesimal distance. Oh my god, my eyes are tearing from the boredom. Why do we need to know this? So wait, what did I just? I didn't like I looked it up because it is. Sorry to be so blunt, but it really doesn't go a lot deeper than that. The ultimate test of any physical idea is whether it agrees with observation. I'm confused. Didn't I just read something else? Answer 1 of 206. In classical sense, all waves have the property that their speed is a constant in any given medium, because the speed depends only on the properties of that medium. Where is this? Let me look up these words. In classical sense, blah 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 blah. Let me look this up. I didn't find it. Find it. It doesn't show up. Maybe here? Where is this? It doesn't find it? So where is this? Okay, let's just Google this. Let's brave. Just this statement. Just search brave just for this statement. In classical sense, all waves have the property of transferring energy without what? Transporting matter through. This is fundamental mechanical wave. Mechanical wave energy is transferred. Electromagnetic. Okay, I think we're done. As far as I know, no one has done this. If anyone has done this, they should have told Einstein. Did Einstein say this? Maybe Einstein said it and no one noticed. Okay, let's read Einstein's original paper. Einstein. Oh my God, my fingers are hurting. 1905 paper PDF on the electrodynamics of moving bodies. I think this is it, or maybe this. Annus Mirabilis. That means Year of the Miracles of Albert Einstein. Ether in Einstein, reading Einstein's 1905 paper on special relativity. Oh my God, I'm falling asleep. Yeah, but this time I have a reason. I barely slept. The Principle of Relativity original papers. Okay. Oh, this it? By Albert Einstein. Oh my God, let's make it much bigger. Okay. Let's look it up. So search for speed. It shows up just once. C denotes the speed of light as opposed to v by Einstein. Wait, is this Einstein's or is it not Einstein's? So Einstein never used the word speed. Okay. For formula. What is formula? Okay. He doesn't use maybe speed, maybe he says velocity. Velocity 53 times. Okay. So that light is always propagated in empty space with a definite velocity, which is independent of the state of motion of the emitting body. These two postulates suffice for the attainment. So it's a postulate. Principle. Schmincipal. Okay, I think we're done. I mean, that's it. It's that simple. It's simpler than simplicity itself. It's so simple. So if you assume like water or any other liquid that doesn't stretch or bend or whatever, which is what I'm assuming the ether is. This is evidence of the ether. Since it's been confirmed, since relativity is the most successful theory ever, then the postulate is confirmed. And since we proved it, we proved ether. We're done. We will raise this conjecture. It's a conjecture, the purport of which will hereafter be called the principle of relativity to the status of a postulate. So he said it before. Okay, examples of this sort. Let's try here. Examples of this sort. What sort? Whatever. Together with unsuccessful attempts to discover any motion of the Earth relatively to the lighter medium. Isn't this Michelson? Didn't he just talk about Michelson? It is known that Maxwell's electrodynamics is usually understood at the present time when applied to moving bodies leads to asymmetries which do not appear to be inherent in the phenomena. What are you talking about? Take, for example, the reciprocal electrodynamic action of a magnet and a conductor. Oh my God, I'm going to go to sleep. In the conductor, I don't care. Examples of this sort, together with the unsuccessful attempts to discover any motion of the Earth relatively to the light medium, suggests that the phenomena of as well as mechanics possesses no properties corresponding to the idea of absolute rest. Okay, so he assumed a vacuum. They suggest rather that, as has already been shown to the first order of small quantities, the same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good. We will raise this conjecture, the purport of which will hereafter be called the principle of relativity, to the status of postulate. I don't know these words like conjecture and postulate. Postulate, I just think it's an assumption, and also introduce another postulate, which is only apparently irreconcilable with the former, namely that light is always propagated in empty space. Oh my God, there he's saying it in empty space with a definite velocity which is independent of the state of motion. Okay, he did not think there is an ether while writing this paper. That's very clear. These two postulates. Okay, we're done. That's it. The introduction of illuminophysics will prove to be superfluous. There you go. Inasmuch as the view here to be developed will not require an absolute stationary space. Okay, I mean, he doesn't like. Okay, provided with special properties. Okay, I mean, we're done. We're done. Assign a velocity vector to a point. The theory to be developed is based, like electrodynamics, on the kinematics of the rigid body, since the assertions. Oh, shut up, Siri. Since the assertions of any such theory have to do with relationships between rigid bodies, systems of coordinates, clocks, like whatever, insufficient consideration of this circumstance. Oh man, difficulties, move bodies. All right, it's whatever. We're done. We're done. We're done. So he just postulated the measuring of C. Everyone measures C the same. It's a postulate because he wanted to get rid of the ether. Maybe he knew that with the ether, he would get this postulate, he would get this conclusion, and he didn't want the ether. I don't know why he didn't want the ether. If he had the ether, he would get relativity directly from the ether. Okay, maybe we should make a short video of this conclusion. Let's prove Einstein's postulate. So this guy never came back. Never came back. Okay, let me let me just take this PDF. This PDF is good to have to wipe your tushy. You should print it and use it to wipe your tushy. That's basically what it's worth. Here it is. Enjoy Formulab. Okay. I think we're done. I think the proof is simpler than can be imagined. Let's go through the proof. Maybe we should have a separate video. Let me see the time. 2 hours and 10 minutes. Okay, I'm going to stop. I'm going to make a new video so that we have a clear video about the proof of Einstein's postulate. I'll make some phone calls first. This is too exciting. I'll see you next show. Bye bye.